Do we get 5 points for being here?
Sure.
Oh, good job, Emily.
I tried to get in where I can.
Okay. Baeyer-Villiger.
Yes.
We've seen that aldehydes get oxidized to carboxylic acids, and let's do that again. And now, do it with the ketone. Because this is one of the few times that we will actually oxidize a ketone. Very rare. So we could pursue this reaction as an aldehyde, but there would be no point to that because we can already turn aldehydes into carboxylic acids other ways. So we're going to use this to specifically turn ketones into esters. Okay, so there are a lot of R's and there are a lot of O's and H's. Let's figure out where what goes where. If I call this R and R1, and then, so R prime and then R double prime, and this keeps the R, this is still R prime, but now I have this. This looks like an insertion. Looks like an insertion. That I put an atom that didn't belong there before in a carbon to carbon bond, and now I have a carbon to oxygen to carbon bond. That type of reaction, like we saw in Grignard's, is called an insertion. It's a little bit more complicated than that. Let's see if we can follow it. So it's going to be the oh, you know what? Yeah, I kind of lied the other day when I said that it is still this oxygen that migrates, but it might not be to here. It might actually be there. We'll figure it out. So let's do this mechanism. All right. So I'm going to want probably to demark what this R group, that R group, and this R group are. And it's really good if if this ketone is asymmetric, because there's going to be a trick about which side of the ketone picks up the oxygen. So let's have an asymmetric ketone Off you go. What do you want to go here for this R group?
Methyl.
Okay. And then on the other side.
Benzene.
So a phenyl group or a benzyl group?
Phenyl.
All right, and then here, let's have this not be the same as either of those, although it doesn't really matter. Okay, so this then gets to be the peroxy 1, 2, 3 method F pro. Peroxy propanoic acid. And this gets to be, name of that. This is acetophenone. Okay. First things first. I'm going to actually back up a step. Acetophenone is in the presence of acid. And the key to so many of our reactions has been protonate the alcohol, or protonate the oxygen. Okay, so I'm going to protonate that oxygen, and now that means this is my electrophile. That carbon is on the losing end of a polar bond, and because that oxygen is now protonated, I don't have to make a negative charge when I attack this carbon. So this double bond is primed to break. It's the weakest thing out there. And the other thing that we've already mentioned is that double bond needs to go. Okay, let's get through this. Now, it's not immediately obvious which of these lone pairs to take, but I can tell you that if we take this one and we work through the mechanism, it looks rational. If we take that one, it starts out looking okay, and then we kind of dead end. We dead end because I attach and I can do things here, but I never can break this bond. And the whole point of this reaction is I have to break that peroxy bond. So just take my word for it right now. We don't have the time today to do them all laid out side by side and say, see, this one's better than the other, but it is. All right, that pi bond opened. Doesn't really matter. I've attached two things together, and it's kind of big and ugly, but hopefully you can see there's a positive charge on that oxygen because it has 3 bonds. That hydrogen has 1, this oxygen has 2, this carbon has 4, that oxygen has 3, this oxygen has 2, that carbon has 4, that oxygen has 2. That positive charge needs to go away.
Can you explain how, like, I'm confused on how that was added, or what happened?
This oxygen is holding on to an oxygen and a hydrogen. going to use its lone pair of electrons, nucleophile, lone pair of electrons, to this carbon. This is a bond that needs to break because that's an electrophile. It's on the losing end of that polar bond. And if we experiment with it, something nice happens. It's in equilibrium. So if the molecule tried this and it didn't work, it could just back out of it. If it tried it with that lone pair of electrons, actually, it would attach and then just shrug and say, I don't know how to resolve what's going to happen next because I have to break this bond. This bond has to go. That's the peroxy bond. Peroxides are unstable to the point that some of them are explosive. That bond has to go. All right. At this point, let's see what we can do to break that bond. Anything I can do to break the bond? Immediately obvious. But it does involve reforming that carbonyl. Now, we can cheat because we already know what the outcome is. We know that I'm going to make an ester and I'm going to make a carboxylic acid. And the carboxylic acid is the easiest thing to see. It's right there. It's this thing here. Which means that bond has to break. Now, if I just made the if I just reformed this and said, okay, here we go. I reformed that. This carbon already has 4 bonds, has to let go of something. I look at this in terms of basicity and say, push the oxygen off. That would be completely rational and true, because you would just back, well, without the proton, that's a reprotonate it and then push back to this. But we're not doing that. What we're actually doing is this. We're migrating one of these groups to attach to that oxygen. And the migration depends on 2 things. Size and ability to hold a carbocation. Methyl carbocations are terrible things. They're really, really awful. In fact, phenyl carbocations are really, really terrible as well. We couldn't have chosen 2 worse candidates to have on either side. When you said benzyl, I should have twisted your arm and said, yes, benzyl, not acetophenone. Let's just make that good. benzyl, because this makes a beautiful carbocation.
I have a question.
Yeah.
What is the difference between a phenol and a benzo?
An additional CH2. Phenyl is C6H5. Benzyl is this. It's benzyl. That is phenyl. All right, so benzyl now, awesome carbocation. So I have no difficulty. All right, gonna make that bond a little bit longer. This bond migrates. The electrons in that bond move. The peroxide bond breaks, and I just made an ester. And I made a carboxylic acid. We have a plus here that I have to get rid of. And I have pluses floating around in solution. So I'm going to get rid of that. And in fact, I can kill two birds with one stone. Just saying, go ahead and do that. And then I get this. That's an ester. And I get a carboxylic acid. Eventually, when I move away from the core. Notable because this reaction can oxidize a ketone. We don't see very many examples of that. Okay, so here we go. Peroxide bond breaks. There's no coming back from that. And this step right here, let's do it in a different color, because we have to talk about this migration. Hydrogens do it best. So if you had an aldehyde, it would just bump that hydrogen off a carbon to hydrogen bond onto an oxygen to hydrogen bond, and you go from being an aldehyde to being a carboxylic acid. Hydrogen is better than things that are good at having carbocations. So tertiary carbocations are better than secondary carbocations, are better than primary carbocations, are better than methyl carbocations. So you get, the trend is just carbocation stability. And then there's an additional trend at the beginning that trumps everything, that is, are you small? Small objects are easier to move. All right, one more. One of my favorite reactions coming up. Everybody at some point should realize this is my favorite molecule. This is my favorite reaction. When I interview candidates for jobs, and I sit them down and I say, what's your favorite mechanism? If they don't have one, they don't get the job. Because they're clearly lying. I used to run a software company. We made chemistry homework.
What the heck?
Huh?
Yeah, what the heck?
Oh, yeah. And you know, we interview people who want to come and be content authors for us or demonstrators for us. And if they don't, you know, that's a sniff test. You say to them, what's your favorite reaction? And if they're not ready with an answer, then you know that they don't love chemistry.
I have an answer.
Yeah.
It's electrophilic additions.
What type of electrophilic additions?
The easy ones.
To alkenes?
Yeah, symmetrical alkenes.
Okay, but those are rule-based. All right. This is probably my favorite. This is a Wittig with a V. And a Wittig does something that we won't ever see again. We are going to couple two different molecules into one new, slightly more complicated molecule. And you know, I've said a number of times, the number of times that we see a new carbon-carbon bond being made in the book, or a carbon-to-carbon bond being broken in the book, very few. We're going to make a new carbon-to-carbon double bond. We're going to take a haloalkane and a carbonyl. Here's the carbonyl. Here's the haloalkane. Let's have this be an X, this be an H. And then this can be R1, R2, R3, and R4.
So you do that just for distinction? That's all that means? I'm like, okay.
I'm going to put this in the presence of some base and a little molecule called a phosphine. And what a phosphine is it's an oxygen scavenger. So this is a phosphine. And I'm going to put that in the base. And you make this. Or you make this. But not and. Either or. Cis or the trans. E or the Z. And it is completely controllable. The stereochemistry in this reaction is completely controllable by our conditions. So essentially, what I'm doing is this. I'm just snipping that out. I'm taking these two parts and coupling them together. So this is a Wittig coupling. It's a type of reaction called coupling. And if you look at the Wittig, there are so many adaptations that now have their own names. So take a carbonyl, and it could be an aldehyde or a ketone, and you take a haloalkane. It has to be a secondary, primary, or methyl. I need that hydrogen. Can't work without that hydrogen. That's what the base is for. The base is going to grab that hydrogen. And without the hydrogen here, it's not going to work. So this needs to be a secondary, a primary, or a methyl. And I make an alkene. And it will be the E or the Z, but not both. All right, let's look at the mechanism. The mechanism occurs in 2 steps, similar to the strategy of what we did with the Spern oxidation. It's going to happen in 2 steps. Step 1 is preparation of the reactive intermediate. The reactive intermediate in our case is going to be called this. That's an ylide. And an ylide is like a Zwitter ion. You know what a Zwitter ion is? Doing biochemistry, you should. The Zwitter ion has a plus and a minus in it. So all proteins, all amino acids, have a plus and a minus in them simultaneously, but they cancel each other out. In an ylide, the plus and the minus are next to each other. So it's a vicinal Zwitter. Lots of vers, Spern, Zwitter, Wittig. I think we're done with the Germanic W's after today. All right, let's see how this goes. Here is the phosphine. Phosphine, like ammonia or a tertiary amine, has a lone pair of electrons. That means it can be a nucleophile. All right, I'm going to make this asymmetric. Now, with the Baeyer-Villiger, we didn't get to use acetophenone, so let's make this acetophenone, because I'm not breaking these bonds. I'm making a new bond right here. Okay. SN2. Phosphorus is like nitrogen in that when it makes a certain number of bonds, it's uncharged, and then when it makes one more than that number, it has to pick up a charge. 3 bonded phosphorus, no charge. 4 bonded phosphorus, positive charge. Here comes the base. So the preparation of the reactive intermediate comes in 2 steps. Addition of the phosphine and then addition of the base. There are a couple of adaptations out there that want you to use a nice big bulky base for something or other. Hydroxide will do.
Will it be strong?
Yeah. This is an ylide. It has a plus and a minus living in the molecule at the same time. two opposite charges in the molecule at the same time make it a Zwitter ion. Having them be vicinal makes it an ylid. There is a resonance structure for this. That if I wanted to put my electrons towards that positive, I could make this. And that is a description that some of the books use to describe our reactive intermediate. I tell you, it's not quite as useful. It's also not quite as true. This is a better description than that, but this is nicer to look at. Here comes the second reaction. Here is the Wittig coupling. All right, so I've used my haloalkane, my phosphine, and the base. Now I'm just going to add the carbonyl. So let's plan how to do this. It depends on what you write down first. We could have this be acetophenone. So this was a methyl and a phenyl. We could have this be acetophenone and then make the choice between just trans and cis, because both would be two methyls and two phenols. That would work. Okay, so let's do that. Nice big long carbon to oxygen bond, right? Because I'm going to need some space. That's the positive end of this molecule, and that's the negative end. I'm going to line my reactive intermediate up so that it's positive and it's negative match. A little bit negative here will line up nicely with the positive. Little bit positive here will line up nicely with the negative on my reactive intermediate, on my ylid. All right, the phosphorus end is holding on to 3 of those, and the carbon end is holding on to a methyl and a phenyl. And although an sp2 carbon would be planar, that's why I've written it in blue, with a carbanion, that's a lone pair of electrons holding that negative charge. This is sp3. This is an sp3 center. It's not flat, it's not planar. Okay, we're going to have the negative thing reach out and grab the positive thing. Right here. I just made a carbon to carbon bond. Those don't happen very often. Don't happen very often at all. Well, the carbon on the top, it already has 4 bonds. So there's 2 ways that we can do this. We can do it this way. That I reach out, I break the pi bond, I localize the electrons on that oxygen, and then in my next step, guess what this negative does? That negative goes and reaches here. Or, the more modern school of thinking says, that actually all happens in one step. Both descriptions have people actively arguing that they're correct, that this makes a negative charge and then that reaches out and grabs the positive. Ultimately, the same thing happens. I make this. A carbon to oxygen to phosphorus to carbon square. This will not survive. This is a strained ring, and this is not going to last very long. But it has played directly into the hands of the people who designed the reaction. Because phosphorus, above everything else, loves to bond to oxygen, loves oxygen. And if you have oxygen in your reaction, in your molecule, and you want to get rid of it, let some phosphorus see it, because phosphorus will take that oxygen away. So I've got a square, and that square clearly needs to break apart. The trick is that this phosphorus wants to bond to oxygen more than the carbon does. The bond from carbon to oxygen is there. It's here. This bond to phosphorus is much, much better. So let's just take it. The phosphorus is going to take the oxygen away from the carbon. Well, that means that this carbon used to have 4 bonds, now only has 3. This phosphorus is going to let go of its bond to carbon. Phosphorus doesn't need bonds to carbon. It wants bonds to oxygen. And I just made an alkene and a phosphine oxide. Okay, question is, which alkene did I make? Made that one, or I made this one. And right now I don't know. But I'm going to reveal to you how you tell. The reason that this works is very, very complicated. From the outside, it looks like a size thing, but from the inside, it is much, much, much more complicated than that. It comes down to these R groups on the phosphorus right here. Are they pushing electrons or pulling electrons? Because it's actually at this stage of the reaction. If I'm pumping up that positive, then the two things come together like this. And if I make it so that this positive is not big, then the lobes don't overlap on this face of the molecule anymore, but they do on that face. So it's asymmetric. If I push electrons in, I stabilize this, and if I pull them out, I stabilize that. Stereochemistry of the alkene depends on which phosphine you use. The cis versus the trans. If you use a phenylphosphine, you make the cis isomer. You write that as PPH3. If, however, you use an alkyl phosphine, like the methyl phosphine, then you get the trans. And we call this PME3. And that seems like just such an easy trade-off. I want one, I do this. I want the other one, I do that. However, it's a little bit more experimentally complicated than that, because this phosphine is non-toxic, white powder. Somewhat oxygen sensitive. Oh. And cheap. But the phosphine, the methylphosphine, is a toxic liquid that is wildly oxygen sensitive. And it stinks. In my old lab, we had multiple fridges. We had a little fridge for the boss's research, we had the big fridge for everybody else's research, and then we had a separate fridge for the phosphines. And if today was the day that you were going to open the phosphine fridge, you tell everybody in the lab, I'm going to open the phosphine fridge at 11:30. And they'll say, make it 12:15, so I'm out of the room. Because they stink. So, this is a white powder. It can be held in the stockroom. You can take the lid off it and look inside to see how much powder is left and put the lid back on. This is a liquid. It comes in a little vial with a screw tap with a septum. And you have to push nitrogen gas or argon in and then syringe out the volume that you need. And it absolutely stinks. You know, onion, garlic, on fire. You feed your dog nothing but onions for a week. And then set it on fire. That's what it's just bad. So now you have a syringe with the phosphine in it, and you put that into your reaction, and you have to keep oxygen out of your reaction flask. And then you put your syringe down in the fume hood, because you're working in the fume hood, of course. And the little droplet of phosphine that's on the end of your syringe touches the paper, and the paper catches fire. That's the fun part. Now you have a fire inside the fume hood, and the fume hood is a chimney. And the paper towel is now floating around inside the fume hood. And what do we keep in the fume hood? All the toxic, flammable chemicals and everybody's experiment. And if that sounds like I know what I'm talking about, it is because I'm one of the few people ever to set fire to a fume hood by doing that exact thing. The droplet from the end of my syringe touched a paper towel, and now the fume hood is on fire. But you've got complete control over which product you make. Okay, we're done.
Allows that acronym.
There's a part where it's just kind of like it says in 5 or 6 portions, so I just like poured it in. And it just like exploded on my lap.
Seriously?
Yeah, Caitlin was there. She was like part of it.
That's funny.
Yeah, it was really bad actually. That was really nice.
What is it that you wanted to go